Hello and good afternoon to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss two important aspects of a computer system, which are organization of a computer system and interrupts. A typical computer system has in it several identifiable units. The units are input unit, central processing unit, output unit, memory unit, and the system buses. To begin with, let us try to discuss the activities that are performed by input unit. Input unit is a unit that is capable of communicating data and instruction from the environment to the system. So, input unit is a unit that is capable of transforming physical data into logical data. For an example, a press of a key on the keyboard is translated into a character in the system. So, the physical movement of a key is getting translated into a character in the system. So that is the way how input unit is capable of performing its operation. So input unit is a unit that is capable of communicating program instruction and data from the environment to the system. This implies input unit is a unit that transforms physical data into logical data. Now the second unit that we have is called as the central processing unit. The central processing unit performs, as the name says, it performs all the business operations. Now central processing unit has in it two identifiable subunits. The subunits are control unit and arithmetic logical unit. Control unit, as the name says, is a unit that controls and coordinates the activities of all the other units that are there in the computer system. Again, I'll repeat it. Control unit is a unit that controls and coordinates the activities of all the other units that are there in the computer system. Now, likewise, arithmetic logical unit is responsible for performing arithmetic and logical operation. Now, the third unit that you have is called as memory unit. Memory unit is a unit that is capable of storing data and programming instructions. In a computer system, there are different types of memories. These includes CPU registers, cache memory, main memory, and secondary storage or hard drive, for an example. Now, CPU registers are high-speed memory that the control unit and the arithmetic logical unit is in direct contact with. So, CPU register is the only memory of all the memory type to which the control unit and the arithmetic logical unit is in direct contact with. So the arithmetic logical unit performs operation based on the instruction and the data that is stored in the CPU register. Now it is also to be understood that CPU registers are onboard memory. Onboard memory basically refers to a memory that is present in the processor itself. So CPU register is a typical example of an onboard memory. Now, as CPU registers are onboard, we cannot have CPU registers of greater size. This implies we have very limited number of CPU registers that is capable of storing programming instructions and data whenever the central processing unit is performing operation. Now the next type of memory that we have is called as cache memory. So cache memory is used in order to supplement the CPU registers. So cache memory is used in order to store frequently used data by the central processing unit. Now there are different types of cache. For an example, you have L1 cache, you have L2 cache, and you have L3 cache. So all of these cache memory, types of cache memory, are used in order to supplement the CPU registers. Then the third type of memory that we have in case of computer system is the main memory. Now the main memory is a memory that is capable of holding all the program and the data that is required by the central processing unit in order to perform operation. So all the programming instruction and the data that is currently being required by the central processing unit in order to perform operation should be present in the main memory. Then we have secondary storage. So secondary storage is a type of memory that is used in order to store program instructions and data that is not being currently used by the central processing unit. Now, as I've already said, these type of memory can be categorized into different categories based on various concepts. For an example, we have volatile and a non-volatile memory. So volatile memory basically refers to memory that loses its content once the power is turned off. And non-volatile basically means a type of memory that is capable of retaining the information that it has stored even if there is a even if the power supply is not there. So main memory is a typical example of volatile memory. So cache is a typical example of volatile memory. Register is a typical example of volatile memory, where secondary storage is a typical example of non-volatile memory. Now likewise, the second way how these memory types can be categorized is onboard memory and offboard memory. So CPU registers are an example of onboard memory. Internal cache is an example of onboard memory, whereas secondary cache, main memory, and a secondary storage device, these are all examples of off-board memory. So onboard memory basically refers to memory that is there within the processor, and off-board memory basically refers to that is something that is outside the processor. So these are the possible ways in which you can categorize the memory type. So again, I'll repeat it. So there are four basic memory types. So you have CPU registers, you have cache, you have main memory, and you have secondary memory. Then we have the output device. So output device is capable of communicating data from the system to the environment back. So it's a unit that is capable of transforming logical data back to physical form. So we have typical examples for input unit, the output unit, and the memory unit. So input unit, you have examples as keyboard, mouse, scanners. So as keyboard, mouse, and scanners are examples of input unit. Output unit, you have printers, display unit, and so on and so forth. So these are examples of input and output unit. Likewise, in case of memory, you have registers, you have cache, you have L1, L2, L3 cache, and then we have main memory, and eventually we have secondary memory. So these are the components to the organization of a computer system. Now let us try to understand a computer system with the help of a schematic representation. So a computer system has in it, as discussed, it has peripheral devices, it has central processing unit, it has memory unit, and it has system bus. Now we forgot to discuss system bus. So system bus basically refers to the channels of communication between various units. So we have control bus, we have data bus, and we have address bus. So these buses are basically channels that are used in order to communicate information to and from the devices. So this is a very simple schematic representation of a computer system. So a computer system has in it the central processing unit, the input unit, the output unit, the memory, and the system buses. Now here it's also to be understood that a computer system can have more than one central processing unit based on the requirement. Now associated with each and every other unit that we have the device controllers. Now, let us try to understand the role of the device controllers. Now, device controllers are capable of managing the associated device. In addition to that, it's capable of establishing or enabling communication between the central processing unit and the devices. Because as we all know, the speed at which the central processing unit may operate and the speed at which the devices that are there may operate may be completely different. So in order to ensure that proper communication takes place between the central processing unit and the various devices, we have the device controllers. So device controllers are capable of controlling the devices and are capable of coordinating communication between the devices and the other units that are there in the computer system, because a computer system is a collection of devices that works at different speed. Now, one of the major limitations of a computer system is that we cannot have a dedicated set of communication channels used or established between various units. So, the communication channels that we have are basically shared communication channels, and these communication channels are to be optimally utilized by different units in order to perform their purpose specific operations. So here, one of the major constraints that is associated with a computer system is that it shares system buses or the communication channel, and it shares memory. So whenever operations are to be performed by the central processing unit or the IO devices, it has to be ensured that the communication channels are being optimally utilized. So one of the major constraints of a computer system is a computer system works with a shared memory and a shared bus. As I've already said, the central processing unit performs its own dedicated set of operations, and IO devices performs its own set of operations. So these operations may run concurrently. So in order to ensure that the computer system as a whole is capable of collectively realizing the desired objective, these devices or these unit has to be properly synchronized. Now, as I've said, with each and every device we have device controllers. So device controllers are capable of controlling the device, and in addition to that, it's capable of establishing communication between the device and the other devices that are there in the computer system. Device controllers are also capable of maintaining local buffer. So whenever interaction is to be established between two different devices that works at different speed, so the buffers that are there comes in handy. So the data from the device is placed onto the buffer at a given speed, and then the data is communicated from the buffer to the central processing unit at a desired speed by the central processing of the central processing unit. The buffers that are there in the device controllers are used in order to maintain local data that is to be communicated between devices that are operating at different speed. So CPU moves the data to and from main memory to and from the local buffer. So data exchange takes place in between the main memory and the buffer that are associated with each and every device. Now, whenever an operation is to be performed by an IO device, right? So the device controller informs CPU or the central processing unit about the operation that is to be performed by causing an interrupt. So device controller informs the central processing unit about its operation by causing an interrupt. So interrupt is a mechanism of letting the central processing unit know that there is some high priority operation that is to be performed on behalf of a given device. So that is what an interrupt is. So interrupt is basically a mechanism of letting the central processing unit know that a high priority process is to be executed on behalf of certain devices. So this is the way how computer system works. So central processing unit performs its own business operations. So once an IO device wants to perform an operation using a central processing unit, so it interrupts the central processing unit to say that there is a high priority task that you need to execute. So this particular process of interrupting or letting the central processing unit know that an operation is to be performed is called as interrupts. So we'll discuss interrupts now in detail. So this is in brief what a computer system looks like. So computer system has in it, again I'll repeat it, it has in it the central processing unit, the memory unit, the IO units, and the system buses. So the system buses are used in order to establish communication between various units. Again I'll repeat it, there are different variants of memory. So you have register, you have cache, you have main memory, and you have secondary memory. Now, let us try to understand what is an interrupt. So as we have already known that interrupt is a mechanism by which you let the central processing unit know that there is a high priority process that is to be executed on behalf of certain devices. So the device controller is capable of making the central processing unit know that there is a high priority task that is to be executed on behalf of a given device. So interrupt, it is a signal raised through hardware or software calling. So either we can have a hardware interrupt or we can have a software interrupt. So it implies we can have both types of interrupt, either raised through hardware signals or raised through software programming instruction. So we can have either hardware interrupt or software interrupt. So whenever there is an interrupt, it implies that it requires immediate attention of the processor for executing a high priority process. So an interrupt is a mechanism of letting the central processing unit know that a high priority process is to be executed on behalf of the device. Now, when a processor receives an interrupt, what does it do? So one thing that a processor might do is processor might ignore the interrupt, or processor might attend the interrupt. So based on the priority of the interrupt, the processor may or may not attend to the interrupt. Now let us consider that the processor attends to an interrupt. So whenever an interrupt takes place and whenever the processor agrees to attend the interrupt, the processor first completes the execution of the current instruction, because processor, while interrupt takes place, the processor may be in the course of executing an instruction. So what does it do? First, it will complete the current instruction that is being executed by the central processing unit. Then once it completes the execution of the instruction that is currently being executed, it stores the content of the program counter and the program status word to the call stack. Now call stack is a dynamically implemented data structure that stores the status of the program. So what are the status of the program it stores? It stores the program counter and the program status word. So once an interrupt has taken place, once the processor executes the current instruction, it stores the content of the program counter and the program status word to the call stack. As I've already said, call stack is a dynamically implemented data structure that stores the return address, because return address is stored in the program counter. Now once the program counter's content and the program status word is stored into the call stack, what we need to do is we need to load the program counter with the address of the first instruction of the interrupt service routine. So whenever an interrupt takes place or whenever a processor is interrupted, it implies that there is a high priority process that is to be executed by the processor. So the set of instructions pertaining to the high priority process may be stored somewhere else in the memory. So now what you need to do, you need to load the program counter with the address of the first instruction of the interrupt service routine. So interrupt service routine is nothing but a set of programming instruction associated with an interrupt. So whenever an interrupt takes place, whenever a processor decides to attend an interrupt, so what does it do? It completes the execution of the current instruction. It stores the program counter, content of the program counter, and the program status word onto the stack, and then it loads the program counter with the address of the first instruction of the interrupt service routine. So as I've said, interrupt service routine is nothing but a set of instructions that is associated with an interrupt, which is to be executed when the processor attends to the interrupt. So every interrupt has with it an ISR or interrupt service routine that gives the description of the task that is to be performed by the processor whenever the interrupt takes place. So we need to load, or the processor loads the program counter with the address of the first instruction of the ISR. Then the processor informs the device that its request has been recognized and the device has to stop disturbing the central processing unit for a request of executing the ISR. So processor informs the device that its request has been recognized and it has to now stop sending interrupt request signals, because it may so happen that the device may continuously raise interrupts which may actually disturb the central processing unit whenever it performs operation. So central processing unit acknowledges that I have received the interrupt and now you need to stop sending interrupt request. So this is the way, in a very simple term, the way how an interrupt is handled by the central processing unit if it desires to attend the interrupt. Now associated with interrupt, we have certain latency. So the overall objective of the processor is to reduce the interrupt latency. Now what does interrupt latency basically refer to? Interrupt latency basically refers to the delay that the processor incurs because of execution of the interrupt. So interrupt latency has two identifiable components to it. So this is called as the context switching time. So the context switching time, the time that is required to switch from the execution of the current instruction to the execution of the ISR. So that is called as context switching time. So here it is represented by T switch. So it's time taken for context switching. So context switching basically means switching mode from normal execution to the execution of ISR. So we require time for that. And then we have time that is required for executing the ISR. So here summation of T execution. So the sum of time intervals for executing the ISR. So interrupt latency is contributed by these two timestamps. So one is the context switching time, and then we have the execution time. Now the context switching time also includes time that is required to switch from ISR to the normal execution. So we have execution, context switching taking place from the normal execution of program to ISR, and from ISR to the normal execution of the program. So here we have two timestamps. One is the transfer time and the other one is the return time, and then we have the execution time. So the overall time or the interrupt latency is influenced by the invoking time, the execution time, and the return time. So that is what interrupt latency is all about. So the overall objective of executing interrupt services are to reduce the interrupt latency. Now we have a very simple schematic representation or a flow representation that tries to represent how interrupts are being managed by the central processing unit. So the first thing that happens whenever an interrupt is raised. So device controller or other system hardware issues interrupt. So device controller that are associated with the device or other hardware system issues an interrupt. The processor finishes execution of the current instruction, as we have learned. Processor finishes the execution of current instruction and then processor signals acknowledgement of the interrupt. So processor lets the device know that, okay, I have received an interrupt and I may process that interrupt at a later point in time. Then the processor puts onto the stack the program status word and the program counter. So processor push does push the program status word and the program counter onto the control stack. Then the processor loads new program counter value based on the interrupt. So based on the address of the ISR or the interrupt service routine, the program counter will be initialized with the address of the first instruction of the ISR. So that is what we have learned. Then save remainder of the processor state information. So it's very important for all of us to save the processor state information because it may be required for a later point in time. Then we need to process the interrupt. Once the interrupt service routine has been executed completely, then we need to restore process state information. Then we need to restore old program status word and program counter to resume normal execution. So this is the way how interrupts are handled by processor. So device controller or other system hardware issues an interrupt. Processor finishes execution of current instruction. Processor signals acknowledgement of interrupts. Processor stores the program status word and the program counter onto the stack. Processor loads the program counter value based on the address of the interrupt service routine. Then it saves the remainder of the process status onto the information. Then it processes the interrupt. Then it restores process state information. Then it restores old program status word and program counter. So this is the way how interrupt is handled by the processor. Now, as we have learned, interrupts can be classified in different categories. So one way of classifying interrupts are hardware interrupt and software interrupt. So some of the interrupts are hardware interrupts, some of the interrupts are software interrupts. So hardware interrupts are interrupts that are raised by devices, whereas software interrupts are interrupts that are raised through software programs or programming instructions. So these are some of the important descriptions of hardware interrupt and software interrupt. So source of hardware interrupt, so generated from an external device or hardware. Likewise, in case of software interrupt, generated by an internal system of a computer with the help of instructions. So here we have INT instruction for generating software interrupts. Now program counter, in case of hardware interrupt, it does not increment the program counter, whereas in case of software interrupt, the program counter is incremented. Priority, so hardware interrupts have lower priority than software interrupt, whereas software interrupt has higher priority than hardware interrupts. So in terms of priority, so hardware interrupts have lower priority, whereas software interrupt have higher priority. Timing, so hardware interrupts are asynchronous in nature, whereas software interrupts are synchronous in nature. Now types of hardware interrupts, so we can have maskable and non-maskable hardware interrupts. So in case of software interrupts, we have maskable and non-maskable interrupts. Now example of hardware interrupts, so as I've said, keystroke depression is an example of hardware interrupt. Mouse movement is an example of hardware interrupt. So we have other interrupts. So we have INTR, RST 7.5, RST 6.5, 5.5 trap. So these are examples of hardware interrupts in case of 8085 microprocessor. Now likewise, all system calls are examples of software interrupt. So we have RST, so RST 0, RST 1, RST 2. So these are examples of software interrupts in case of 8085 microprocessor. So these are some of the ways in which you can distinguish between hardware interrupts and software interrupts. Now another way of classifying interrupts are vectored interrupts and non-vectored interrupts. Now vectored interrupts basically vector basically means address. So vector interrupts are interrupts with which we have address of the ISR associated. So whenever a processor is interrupted by a vectored interrupt, processor knows where the ISR of the interrupt lies. Whereas in case of non-vectored interrupt, the processor does not have information about the address of the ISR. So we need to provide the address of the ISR whenever non-vector interrupts a microprocessor or the central processing unit. So that is the key distinction between vectored and non-vectored interrupts. So vectored interrupts are interrupt with which the address is associated or the processor knows the address, and non-vectored interrupts are interrupts with which for which the processor does not know the address and the address has to be supplemented. So vectored interrupts are those with which a fixed vector address associated, that is the starting address of the interrupt service routine. So we have trap, then we have RST 5.5, 6.5, 7.5, RST 0, 1, 2, 3, 4, 5, 6, 7. So these are all examples of vectored interrupts. So here the address is also associated. So address for trap is 24H. Address for RST 5.5 is 2CH. RST 6.5 is 34H. RST 7.5 is 3CH. Likewise, RST 0 has vector address as 00H. So likewise, RST 7 has vector address as 38H. So associated with each and every vector interrupt, you have the vector address or the address of the ISR. So here what we have is we have a vector table associated with the interrupts. Likewise, we have non-vectored interrupts. So non-vectored interrupts are interrupts with which for which the processor does not know the vector address, so where the vector address is not predefined. So the interrupting device gives the address of the subroutine for these interrupts. So INTR is a typical example of non-vectored interrupt in case of 8085 microprocessor. So these examples are in correlation with 8085 microprocessor. So this is the way how you distinguish between vectored and non-vectored interrupt. Now, next way of categorizing interrupts are maskable and non-maskable interrupts. So maskable interrupts basically refers to interrupts that can be ignored by the processor, or that can be masked or delayed by the processor. So that is what maskable interrupt is. So maskable interrupt is an interrupt that may be ignored or delayed by the microprocessor, whereas non-maskable interrupts are interrupts that cannot be ignored by the microprocessor. So once the interrupt takes place, it cannot be ignored. So maskable interrupts are those interrupts that can be disabled or ignored by the microprocessor. So INTR, RST 7.5, 6.5, 5.5 are examples of maskable interrupt in case of 8085 microprocessor. Whereas non-maskable interrupts are those interrupts that cannot be disabled or ignored by the microprocessor. So trap is a typical example of non-maskable interrupt. So in today's class, what we have learned about is we have learned about the computer system organization. So we have learned about various units that are there in a computer system. We have learned about the significance of the various units. Then we have learned about the role of the various device controllers that are there associated with the device. We have learned about the significance of the system buses in a computer system. Then we have learned about how the device interacts with the central processing unit by raising interrupt. Then we moved on to interrupt fundamentals, where we discuss the mechanism of interrupt and its handling in a very simple context. Then we learned about the significance of interrupt latency, and then we did learn about the way how the processor handles interrupt with the help of a schematic representation. Then we tried to classify interrupts into either hardware interrupts or software interrupts, where we learned about the description of the various interrupts, taking into account sources, program counter, priority, timing, types, and examples. Then we moved on to the next way of categorizing or classifying interrupts, that is vectored and non-vectored interrupt, where we learned that vectored interrupts are interrupts with which the vector address is associated, whereas non-vectored interrupts are interrupt with which the processor, or for which the processor does not know the vector address, so the vector address has to be supplemented when the interrupt takes place. Then we moved on to the next way of categorizing or classifying interrupts, that is maskable and non-maskable interrupt, where we learned that maskable interrupts are interrupts that can be ignored or disabled by the microprocessor, whereas non-maskable interrupts are interrupts that cannot be disabled or ignored by the microprocessor. So here we'll call it a day. Thank you very much.